Imagine if scientists found out Earth was near the path of a gigantic meteor. How could we escape the fate of death? Well, you would probably say something along the lines of, we could nuke away the asteroid. Or maybe, fearing death is stupid. Let's embrace extinction.
Our team thinks a little differently. According to some scientists, it would be possible to move not only Earth itself, but also the rest of the solar system away from the route of destruction using a solar engine.
In the hypothetical case of a disaster like this, Dr. Leonard Shkadov proposed in his paper the first prototype of a stellar engine, a device that would make the Herculean task of moving our entire solar system feasible. The concept of the structure isn't as complex as it may seem. In simple terms, what a stellar engine would do is harness the radioactive energy emitted by a star, in our case, the Sun, and use that energy to propel it to another place. The objects in its orbit would naturally follow it due to its gravitational force. In order to understand how such a structure would be possible, we first have to take a look at the inner workings of a typical star. There are two types of nuclear reactions, fission and fusion. Nuclear fission is a radioactive decay process in which the atomic nuclei subdivide, producing very large amounts of energy. Fusion, on the other hand, is a reaction in which two or more atomic nuclei get combined to form one or more different atomic nuclei and subatomic particles, releasing even larger amounts of energy. This happens because the element, or isotope, created is more stable than the previous one. In the average star, Sun included, fusion is the name of the game. The process of energy liberation from a star can be summed up in three steps. First, hydrogen atoms collide until they form hydrogen 2, or deuterium, through beta decay. This reaction releases tons of energy because the deuterium is more stable than hydrogen. Second, the deuterium collides with a free proton and forms helium-3. This reaction is also very powerful because helium-3 is more stable than deuterium. Third, the helium-3 atoms collide with each other to form helium-4, a highly exothermic reaction for the same reasons as the two previous steps. All of this nuclear energy gets constantly released by stars like our Sun in the form of highly energized protons, and this is the energy that we'll be using to propel our planetary system.
The engine that Shkadov proposed in his paper is nothing more than an enormous concave mirror. According to the laws of reflection, when a ray of light passes through the focus of a concave mirror, it is reflected parallelly to its principal axis. This means that if the Sun was placed and maintained at the focus of a giant mirror, part of its light would hit the mirror and be reflected in a single parallel set of rays. The photons in those rays carry quite a bit of momentum, which would get transferred to the star in the case of a collision. Since those collisions would be very frequent, the Sun would be propelled by their combined force, albeit very slowly. Another important detail and a limitation of this model is that to avoid burning any planets with the mirror's concentrated light, it could only be placed at the Sun's poles, allowing only for up and down movement. It should also be noted that this mirror wouldn't be spherical but parabolic. This means that we can use the same formula to calculate its focus, which we should know where the Sun needs to be placed in relation to the mirror. In order to derive the appropriate formula for this situation, let's consider a vertical light ray reaching the mirror surface at a point P. The ray suffers reflection and intersects the principal axis at a single point. That's the focus of the mirror, which we'll call F. Let's name some other points. C is the point where the normal at the P point intersects the principal axis, and Q is the orthogonal projection of P onto the axis. Let's also name the angle of incidence of the ray theta. Due to the law of reflection, the angle FPC is also theta, and due to the rule of the interior alternates, FCP has that value as well. Basic geometric considerations thus lead to the fact that the angle QFP is twice as large as theta. Using certain trigonometric relations, we can then find out that the segment FQ is given by the ratio between the horizontal distance x from the ray to the principal axis and the tangent of 2 times theta. Summing this ratio through the height y of the point P gives us the focal distance. Substituting the formula for the tangent of the Sun in that equation gets us to this final formula. And something you might notice right away is that the position of the focus actually depends on the angle of incidence of the light ray. That means the mirror actually has multiple focuses, but fortunately the sun is sufficiently large to cover them all.
In conclusion, with Shkodov thruster, it's possible to move the Earth by moving our entire solar system. Even though we can only move up or down, this gives us plenty of courses to avoid supernovas, meteor rains, and collision routes. Maybe, by using this technology, we will be able to place human colonies on extrasolar planets without ever having to face long travels in the vacuum of space. However, our space mirror is not the fastest engine we could build. The Shkodov thruster is only a Class A engine. Other, more sophisticated models could move faster, but they require more time-consuming explanations, so leave them out of this video. Thank you for your attention.